All right, we're going to continue with section 14.4 in this video, and we're going to do some exercises from the textbook. So we're on page 936, and we're going to start with number 19, which says in exercises 11 through 19, evaluate the integral. Now they don't have it set up for us though, so we have to actually set up the bounds ourselves. So it's the triple integral, over D. Triple integral over D of 3xy dv, where D is the solid region bounded below by the cone z equals the square root of x squared plus y squared, and above by the cylinder x squared plus z squared equals 1. So now I mentioned in 14.2 that we would always, when we were talking about double integrals, we would always sketch our 14.1, we would always sketch our region. Now for triple integrals, our region actually is a three-dimensional region. So we won't usually sketch that three-dimensional region. What we'll do is we'll sketch that three-dimensional region projected down into or projected back or left into one of the coordinate planes. So I'm not going to sketch the region D, but we still are going to use the approach that we use for double integrals, where we had figure out top, bottom, sides, all of that. Now the top, bottom, sides though is all of that is going to be part of our bounds, whereas before the top and the bottom were part of our integrand, but now the top and the bottom become that inside integral right there. So we're still doing the same thing we did for double integrals with the top, bottom, sides. Just remember that the integrand is not determined by the top and bottom. The integrand is going to be given to you, or it will be apparent from the nature of the problem. It's a volume problem, and I'll talk about those in a little bit. All right, so before we have integrands and bounds. Now the information they gave us is just to find bounds, not the integrand. So now our bounds, D is a solid region bounded below by the cone z equals this and above by the cylinder. So they give us our bottom is z equals the square root of x squared plus y squared. Our top is x squared plus z squared equals 1. X squared plus z squared equals 1. And then our sides, we still need sides. And we'll remember, if you're just given a top and a bottom, the way you find your sides is you intersect the top with the bottom. So our quote unquote sides is top intersected with bottom. All right, so now to find our sides, we're going to intersect these two things. So we can just take this z and substitute it in right there. And so z squared is just x squared plus y squared. So when we do that, we just get x squared plus x squared plus y squared equals 1, or 2x squared plus y squared equals 1. All right, so the sides, those are going to determine the bounds for these outside two integrals. So we're just basically doing the same thing. The sides is basically the same thing that we would do for double integrals, and that's what we want to sketch. Is we're going to sketch that two-dimensional region of the sides. The top and the bottom are just going to tell us the bottom is going to give us the lower bound on this inside integral. The top's going to be the upper bound on that inside integral. So let's sketch the sides so we can figure out what the bounds are on these outer two integrals. So what do we have here? So this is going to give us an ellipse. You can look at this. You can go through a couple of different ways to try to figure out what the ellipse is going to look like. Just substitute in a y equals 0, see what you get for x. Substitute x equals 0, see what you get for y. Now, the ellipse form is x squared over something, or x squared over a squared plus y squared over b squared equals 1. But you really don't have to worry about all of that. You just have to plug in some values, and you all should kind of know from quadric surfaces when I talked about conic sections there that this would be an ellipse. But as you're going through these problems in your textbook, just go on Desmos if you're not sure, and the more you put things in there, the more you become familiar with them. So if we do x equals 0, we get y is plus or minus 1. Actually, what are we going to get for y equals 0? So actually, I'm going to make this a little bit bigger. Do this. All right, and then for y equals 0, we're going to get x squared equals 1/2, or x equals plus or minus 1 over root 2. So let's say, I don't know, right there, 1 over root 2. Now, in the past, oops, it's way too far over. In the past, our sketches may not have been that important. In this one, the sketch itself, how well we do, is not important, but the values we get, we do need to know what these are. So our picture may not be the prettiest, but that's okay. So we get this ellipse. Now with this is, we took whatever our region is that we had, and we smashed it down into the XY plane. So this is what we would have. So now we look at this, is this a type 1 or a type 2 region? So we could do it as either. It's both type, and when I say type 1 or 2, when we're talking in 2 dimensions, I'm talking about Roman numeral 1 and Roman numeral 2. So we can do this either way. Let's just go with our convention where we normally go from function to function in the y direction. So now let's take this and solve this for y. If we solve this for y, we're going to get y squared equals 1 minus 2x squared, and then take the square root of both sides. We're going to get y equals plus or minus the square root of 1 minus 2x squared. So now we have our top function. This right here is y equals the square root of 1 minus 2x squared. Not this top, sorry. When I say, I mean top of this thing. And then down here, that's y equals negative square root of 1 minus 2x squared. And then we're going from constant to constant. X goes from negative 1 over root 2 to positive 1 over root 2. So now let's put together our region D. So D, can I fit this on one line? We'll try. D equals the set of points x, y, z, such that what goes from constant to constant, x goes from constant to constant. So x goes from negative 1 over root 2 to 1 over root 2. And actually, before I finish this, because I don't want to forget, so this region that we have right here determines that because we took and we projected into the XY plane, that immediately tells us that we're type Arabic numeral 1. We chose to do this as type 1, comma, Roman numeral 1, but it also would be correct to do this as a type 1, Roman numeral 2, where if we chose to solve for x and x and go from constant to constant in the y direction. Either one of those is fine. Now we're doing that one. So now y goes from negative square root of 1 minus 2x squared. 1 minus 2x squared. Sorry, if I'm writing small, I'm trying to squeeze this all in where you can see it. And then y goes up to the square root of 1 minus 2x squared. And then z is not represented here. It's represented up there. And we have top and bottom there. So we'll solve these for z. So it says the bottom is this and the top is going to be this thing that we have right here. So now this is two different functions if we solve that for z. So we have to keep that in mind. And some semblance of visualization kind of becomes necessary here. So I'm going to do a little quick sketch to see, so that we can see what of those two functions we're going to take there. Now we're going to take the positive of the two functions, and probably that's the natural thing for us to do, but this right here is a cone, and this z is always greater than or equal to 0. So this is not, normally I would not sketch this, but I'm going to just so we have an idea. So whatever, we have some cone. And this cone is always greater than or equal to 0, whereas this cylinder that we have right here, that cylinder, it does go below the xy plane. So remember, that cylinder is a cylinder that runs along the y-axis. So it's going to be something like this. What that cylinder will look like. And the cone is like this. So we know that we're above the cone and below the cylinder, which says that we're going to take the positive z from here. But it's perfectly reasonable to have, on the other hand, something that look like this. I mean, this is not what our problem looks like, but whatever we could have, say for instance, let's just use a cone again, that's shifted down, a cone like that. In this case, we will use the bottom z, or the negative z of the cylinder. In this case, we use the positive z on the cylinder. So that's why I said some level of visualization kind of is necessary to ensure that you use the correct function out of here. Because this z that we have is greater than or equal to 0. We know that the setup is like this. It's not like that. So in this setup right here, the region would be, the three-dimensional region would be that thing. Sorry, these are very rough sketches. In this scenario, the three-dimensional region is that little thing right there. So kind of have to keep some of those things in mind. So now when we solve this for z, we end up getting z equals plus or minus the square root of 1 minus x squared, but we only want the positive part of that because we are looking at the top half of this cylinder cutting off that cone. So our z, I don't think I can fit that in there. I'm going to have to go to the next line. Sorry, I'm going to put my z's down on the next line. So z varies between square root of x squared plus y squared, x squared, sorry, plus y squared, and what did I just say? Square root of 1 minus x squared. And then we close our little set brackets. All right, so that's our region D. So now setting up our integral, we always go, the function of two variables has to be on the inside integral, the function of one variable, middle integral, constants, outside integral. So we end up with the integral from negative 1 over root 2 to 1 over root 2. And then from negative square root of 1 minus 2x squared, negative square root of 1 minus 2x squared, up to the square root of 1 minus 2x squared, 1 minus 2x squared, and then the inside integral, square root of x squared plus y squared, up to the square root of 1 minus x squared, square root of 1 minus x squared. Our integrand was 3xy. There it is, sorry. So our integrand is 3xy. When we check, what are these? Those are z's. So dz. What are these? Those are y's. So dy. And what are these? Those are x's. So dx. That would be our order of integration for that one. So for second time, I'm not going to go through and integrate this, but it's a good exercise for you all to try. But notice, if you can do a single integral from calculus 1, once you've been introduced to a double integral and the approach there, then you can do that. Triple integral is the exact same thing. So now at this point, you know, okay, I'm going to integrate with respect to z first. So that would be 3xy times z. I put these in for z. Then from there, whatever I get there, integrate that with respect to y. Put those in for y. And whatever I get there, integrate that with respect to x, put those in for x. So if you can do a double integral, you can do a triple integral, a quadruple integral. It's just the same iterative process, which is why we call this an iterated integral. All right, so I'll stop this video here, and I'll do a couple more examples of some 14.4 problems in the next video.